morning one and all. So in the last class we have seen two types of random processes. They are triples, which means strict sense stationary, and the next one is wide sense stationary. Now this is the autocorrelation function of a double SS process. It depends upon the time difference or time shift tau. What is tau? It is T2 minus T1, or you can also write T1 minus T2. So if it is triples, obviously it is double SS, but converse may not be true. It is true if and only if it is a Gaussian process. In case of Gaussian, if it is double SS, it is also triples. Now, so I have shared some videos of NPTEL. In those videos, so the professor has discussed about this power spectral density. Now I will briefly go through them. So for every random process, we have a PSD. PSD means power spectral density. So it is denoted with Sx of f. It is in the frequency domain. Now what is the formula? Simply it is the Fourier transform of what? Autocorrelation function or self-correlation function. This is the Fourier transform pairs ACF, and this is PSD. They are Fourier transform pairs, which means if you take Fourier transform to ACF, you get PSD, and if you take inverse Fourier transform for PSD, you get ACF. Now these are some properties. It is always positive. It's a real quantity, and it is symmetric in frequency. This is symmetric in frequency. What next? Yeah, so this is the inverse Fourier transform. Inverse Fourier transform of PSD is ACF. Now this is very important. If you keep tau equal to 0, you get this. No, if tau equal to 0 means e power j0, that is e power 0, that is 1. Now what is this? Nothing but the area under PSD over entire frequencies. So that is nothing but ACF at 0 or RXX at tau equal to 0. Now what does this indicate? RXX of 0. Generally, if you go back, what you written here? RXX for double SS random process. What you written? Yeah. In this expression, keep tau equal to 0. What do you get? It implies expectation of what? X of t whole square. Isn't it? So, if tau equal to 0, RXS of 0 means expectation of x of t whole square. So, it is nothing but power of a random process. Actually, it is the second moment. Okay, it is indicating power. Second moment indicates power. This is very important. Or how to get power? First find out power spectral density and take area under it. Okay. Yeah. So the power of a random process x of t equal to area under PSD over entire frequency ranges. First find out PSD, take area under it over entire frequency ranges. Entire frequency ranges means minus infinity to plus infinity. Otherwise, so if you want Rx of 0, that is nothing but expectation of x of t whole square. It indicates power. Okay. Otherwise, what is area under PSD is nothing but power. Please remember like this. Area under power spectral density is power. If you take area under entire frequency range of power spectral density, you get power. In the same way, if you take area under energy spectral density, ESD means what? Energy spectral density. What do you get? You get energy. Yeah. So these are some of the things. Yeah. So next thing is what will happen if you pass SSS random process through LTI system? You take like this. A LTI system with impulse response h of t. You are passing a random process x of t, which is obviously SSS. What is y of t? What is y of t? So y of t is also SSS process. If x of t is SSS, y of t also SSS. So that is very important. So these are all some derivations. I have shared video. Please go through it once. And furthermore, so the ACF of output is ACF of input convolution h of tau convolution h of minus tau. Is very important. Finally, so output PSD equal to input PSD into h of f whole square. What is h of f? So if you remember, we have system with impulse response h of t. Now if you take Fourier transform to this, you get h of f. We call it as the transfer function or frequency response of a system. So mod of this, please remember mod whole square. So this is very important. Okay. Now, so let us take simple example. So determine the ACF of the process x of t equal to r cos omega t specify where we assume that random variables r and pi are independent and pi is uniform in the interval minus pi to pi. So read the question properly. So let us solve this. So they are given a random process, that is x of t equal to r into cos omega t plus pi. In this, which are two random, this is random, it is also random, which means the amplitude of this cos waveform is random as well as phase is also random, but the phase follows uniform distribution. Uniform in the range of minus pi to pi. Now what it is, PDF would be, so pi, what do you get? Sorry. Okay. So let me draw another figure. So what is the PDF? They mentioned that it is uniform from where to where, minus pi to pi. So from minus pi to pi, obviously this would be 1 by 2 pi because it is uniform, no? Now this is pi, this is f pi of phi. Now r is also random. One more thing is what? These r and pi are independent. They mentioned that both are independent random variables. Now we have to find out ACF of x of t. First of all, what is ACF notation? We write this as Rx of t1 comma t2, whose formula is expectation of x of t1 into x of t2. Now what is x of t1 and x of t2? X of t we know. What is r into cos omega t plus phi? Here x of t1, x of t2. What is x of t1 and x of t2? Can you guess? X of t1 into x of t2. What do you get? You get r square into cos omega t1 plus pi into cos omega t2 plus pi. Isn't it? Now here, so what we can do? It is something like cos a plus cos a into cos b. This is a, this is b. What is a? Omega t1 plus pi. What is b? Omega t2 plus pi. So what is expansion? Cos a into cos b. R square, that is common for both. R square by 2. You can write. Yeah. So you can say cos a plus b plus cos a minus b. Isn't it? So I hope you are okay with this trigonometrics. Cos of a plus b, which means a plus b means what? Omega t1 plus omega t2 plus 2 pi. Is it okay? Omega t1 plus omega t2 plus 2 pi plus cos a minus b. What is cos a minus b? Cos a minus b. Omega t1 minus omega t2. Pi pi cancels. Cos omega t1 minus omega t2. Okay. Now, so this is, remember, this is x of t1 into x of t2 only. But what is ACF? This ACF. You should take expectation to this product. Then yeah. So before doing so, so here what is given is this r and this pi are independent. So if two random variables are independent, what you can say? Expectation of xy equal to expectation of x into expectation of y. So now what I do is I'll take like this. So 1 by 2 outside, expectation of r square, is it okay, into expectation of this quantity. Okay. I am writing separately because they happen to be independent. Omega t1 plus, sorry, this should be cos, no, cos omega t1 plus omega t2 plus 2 pi. This is one quantity. Is it okay? I am applying expectation to this expression. But here we have two random variables r and pi. They happen to be independent. So that's why I am writing separately. Plus, what another quantity you can write? Of expectation of r square. The second quantity. What is that? Expectation of cos of omega t1 minus omega t2. Now, so expectation of r square, we don't know anything about this r. But what we know? We know about this pi. Pi is a uniform distribution random variable. Omega are constant. So simply you need to calculate in the first, let me call this the first one. This is the first one and this is the second one. This is second, enter thing is second one. So let us call, what is expectation of cos of omega t1 plus omega t2 plus 2 pi. Can you guess it? Can you find out this? What is that? So here, what is the random variable? This pi. Is a PDF 1 by 2 pi. So 1 by 2 pi PDF minus pi to pi, this quantity cos of omega t1 plus omega t2 plus 2 pi d pi. Can you calculate this? You get 0. This becomes 0. means so this quantity is 0, which means entire quantity is 0. So the first equation is entirely 0. Now coming to second. In the second, so this cos omega t1 minus omega 2 is a constant. Why? Because it is independent of r and pi. It neither contains r nor pi, isn't it? Because r and pi are only two random variables. Omega is not a random variable. Okay. Now anyway, so if expectation of any constant is the constant itself. So what is the answer finally? The answer is half of expectation of r square into cos of omega t1 minus omega t2. This is the answer. Okay. Yeah. So if the processes happen to be Gaussian, it is always given as WSS, wide distance stationary, which means it is a constant mean and ACB is function of tau, that is a time shift or time difference. So this is things already. How to find variance now? What is variance? So it's very important. What is variance? So expectation of x of t whole square minus mean square. But what is this? Rxx of z, just now we have seen. Okay. Now, so white noise. Yeah. So we have some kind of noise called white noise. A random process is white if it is WSS and ACF should follow the form of this form. Okay, here we have white noise. Why we call it the white? White noise is white random process. Why we call it noise? White. Here it should be WSS, which means first of all double SS, which means wide distance stationary, and if it's ACF, ACF means auto correlation function Rxx of tau equal to n naught by 2 into delta of tau. If the ACF is of this form, then it is called a white noise. So can you draw this? Obviously this is a delta function. It is defined only when tau equal to 0. Otherwise it is 0, isn't it? This is the ACF of the given white noise, isn't it? Now, but we know that what we know, ACF and PSD are what? Fourier transform pairs, which means if you know ACF, you can find out PSD and vice versa. Here, what I know, ACF is known to us. What is the PSD? Which means PSD means Fourier transform of ACF. Here, I know ACF. That is, what is the Fourier transform of n naught by 2 into delta of tau? You know, n naught by 2 is a constant. Now, what is the Fourier transform of delta of tau? It is 1. N naught by 2. This is a PSD. So, n naught by 2 is a constant. Then, what is the PSD? So, PSD is in frequency domain. I told you already. X S of F. It is called PSD. Power spectral density. Now, here this PSD X F equal to what? N naught by 2, which is a constant always. It is a constant. Then how to draw this? What do you get? F. This is the PSD, whose value is N naught by 2. Isn't it? PSD of white noise is this for all frequencies. This is the ACF of white noise. This is the PSD of white noise. Okay. Now actually, what is the white color? White light, not color, white light. How to get white light? If you mix red light, green light and blue light in equal proportions. If you mix red, green, blue lights in equal proportions, or if you mix them uniformly, you get white light. Is it okay? Now, so why it is called white noise? Why it is called white noise? White because in the PSD it treats all frequencies uniformly or equally. It does not discriminate the frequencies. It is same for all frequencies. It treats all frequencies uniformly, just like white light. What is white light? If you mix these three colors in equal proportions, you get white light. White light is a uniform combination of all these lights. In the same way, this noise is uniform for all frequencies. So that's why it has got name white. So uniform over entire frequency range similar to the white light. It is called a white noise. What are the properties of white noise? Its PSD is like this. Please remember it is called two-sided PSD. What is called? Two-sided PSD. Please remember this is very very important. Two-sided power spectral density. Why two-sided? Because it is taking care of all sides. I mean two sides, positive as well as negative. We call it by 2. This is frequency. So we have one-sided PSD also. One side means only positive side. Then what do you write? F. Generally it is not that relevant here, but this is called N. We write only N naught. This is one-sided. But so in all the communication literature, we use this PSD. If they say PSD, by default it is two-sided. By default it is two-sided. If they simply mention PSD, it is two-sided. If they mention specifically one-sided, you consider this. Okay. Now white noise as the autocorrelation function, which is defined like this. No need to write tau or delta of tau anyway. This is the ACF, autocorrelation function. Obviously, if you take the Fourier transform, you get PSD, which is happen to be a constant. That's it for all frequency ranges. Now here N naught by 2. Generally we mention PSD, power spectral density with N naught by 2. They'll give you this value of N naught by 2 or the value of N naught. Or simply they say that the power spectral density is so much, which means they'll give you N naught by 2 value. So what are the units of this? Units. What units of PSD would be? Power per frequency. Power spectral density, which means power per frequency. Power for unit frequency. Obviously, power means watt. Frequency means hertz. So units will be what? Would be watt per hertz. They'll give you this value of N naught by 2. Yeah. So you know white is white when it is called white, and Gaussian if it is follows Gaussian process noise. Now this is very very important. This is a nothing but a communication system. Okay. What will happen is, so when you transmit x of t, through a channel. Now noise will be added to the original signal and output will be sum of two things, your signal plus noise signal. Now x of t is called transmitted signal, y of t is called received signal, n of t is called Gaussian noise. You might have seen, you might have experienced these things. Suppose, so if you're talking on a if you're talking on a mobile phone, sometimes you may receive some unwanted disturbance, that is called noise. Okay, so what is the original signal? You are talking to your friend, so that is your wanted signal or your original message signal, that is being added with noise. What you receive is a corrupted signal or some disturbance. So if you take any communication system, what happens is, what happens? So you transmit something. This is your original signal. But so because of channel, noise will be added. Finally, what you receive is not x of t. What you receive is your original signal x of t plus some noise n of t. Okay. Here. So what is this noise? It is white noise. White Gaussian noise. Why white? Why white? Because this noise treats all frequencies uniformly. Okay, Gaussian, because generally it follows Gaussian process. And there is one more thing, that is called additive. Why additive? Because it is adding to the original signal. It is not multiplying with original signal. It is not dividing or subtracting with original signal. This noise in by nature is additive, which means it is getting added to the original signal x of t. Generally, when you transmit something, noise will be added to that signal. That's why additive. Simply, so they will say like this. Consider additive. The noise is additive in nature. White. It treats all frequencies equally. Gaussian. Generally, noise follows Gaussian process. Noise. So this is the definition of the general noise, means this is a noise. Generally what we call AWGN. Simply the acronym is AWGN, which means they are mentioning about a noise. Additive white Gaussian noise. Noise is additive in nature. It is white, which means it treats all frequencies equally. It does not discriminate between frequencies, and it is following Gaussian process, and it is a noise. Obviously, noise means unwanted signal. Okay. So this is the AWGN. So please remember this. You will encounter this term very frequently in your future courses. AWGN stands for additive wide Gaussian noise. This is a description of a noise. Simply I could have said noise, but you should not say noise. You must say AWGN, additive wide Gaussian noise. Okay. So this is a Gaussian process and it is white in nature. Okay. Now, so let us take a simple example. White noise with a PSD, which means they gave us what? N naught by 2. How much? 10 power minus 6. What are units? Watt per edge. They mentioned it is white, so that's why you can draw this figure. So it treats all frequencies equally. How much noise? 10 power minus 6 watts per edge. Okay. Passed through a ideal differentiator. Then output of the differentiator passed through a ideal low pass filter of cutoff frequency 10 Hz. Then noise powered output of low pass filter is. Now read the question properly. What happened? What they're doing? So here they're doing like this. They have a system. So they're doing two important modifications. What are they? First, they're passing through differentiator, ideal differentiator, and later a low pass filter with a cutoff frequency of 10 kHz. Now here x of is input, y of is output. So this is the systematic view. But what we know, what we know in the question, white noise with a PSD. Now this is noise. There, this is a noise. They mentioned that this is a noise. What is x of t? Is a noise. It has got a PSD. They gave us the PSD of this noise. How much? 10 power minus 6 watts per hertz. It's a white noise. That's why I'm writing this PSD. Is it okay? Now what they're asking? Question. The noise powered output of the low pass filter. That is very very important. They're asking at this point what is the noise power. Now the moment you come across this noise power, the moment you come across power, please remember power means area under PSD. Is it okay? So not only this, what is the probability? Area under what? Probability density function. Density. Okay? Area under probability density function is probability. Area under power spectral density is power. Area under, suppose area under energy spectral density, it would be energy. Simple rule. Remember these things. They're very very simple things. Okay. Now, which means at the output side you need power. You have to calculate power, which means by default power means area under PSD. Output PSD. You must know what is the PSD at the output of the system. Now, so you might have recalled this formula. PSD of output equal to PSD at the input side into what? Mod h of f whole square. I told you this is very very important formula. So here we know this. This is the PSD at the input side. What is this? This is the PSD of input. We know the systems. They're asking what is the power at the output side. Now let me do like one by one. We have two systems. Okay. First, so this is the PSD of the input noise. 10 power minus 6 watts per hertz is a frequency. Now this is being passed through a system. The system is the ideal differentiator. Now what will happen to the output PSD? I'm taking one by one. I have two systems, a ideal differentiator and a low pass filter. Let me do one by one. So what will happen? So here, so if you recall, what is the Fourier transform of differentiator? What will happen? So let me take this h1 of t. So this is h1 of t. By h1 of t, we have two systems. So h1 of t is a differentiator d by dt. What is h1 of f? It is j omega. Plus or minus, I'm not sure. You just find out. But what is mod h1 of f? What is mod of j omega? Is omega. What is mod h1 of f whole square? Which means omega square. Omega means what? 2 pi f. Which means 4 pi square into f square. Now, so what is the output PSD? So PSD of input side into what? 4 pi square into f square. Now here, otherwise, if you are not okay with this, simply you can call this as simply what? This is nothing but omega square. Anything is okay. But so can you draw omega square? It would be parabola, something like this. I am not good at drawing. Please bear with me. Is it okay? Now, so we have done with first system. What next system? Low pass filter. So low pass filter. So here low pass filter. I am directly writing the low pass filter frequency response H2 of f. I am directly writing because for low pass filter they did not give the transfer function. They directly gave us it is ideal low pass filter with cutoff frequency how much? 10 kilohertz, which means minus 10 here, 10 here. So what is the mod of this? It is not required because it is real. What is this whole square? What is h2 of f whole square? It is same. This is 1, no? Here it is 1. So what is h2 of f whole square? It is same. Okay, which means so mod is not required and h2 of f mod is okay. Whole square equal to this low pass filter. Is it okay? Now, so what output PSD now? So input PSD into 4 pi omega square into this figure. Okay. So let me write properly. So PSD at the output side equal to PSD at the input side into omega square. I am writing omega square and into this low pass filter. Otherwise H2 of f whole square. Isn't it? So this is the first system, this second system. This is the first system, this second system. But what is h2 of f whole square? It is this low pass filter. So but omega square is a parabola like this. Now if you multiply these two, what do you get? This into this, 1 into 2. What do you get? Any guesses? So we are multiplying these two. So one is omega square. Next one is what? This. F or omega, no problem. What do you get? You get like this. Figures are not required, but I am just writing for your understanding purpose. This is omega square from where to where? Minus 10k to plus 10k. Yeah. So what input PSD? So into 10 power minus 6 watts per hertz. So this finally PSD at the output side. But in the question, they did not ask what is output PSD. They ask power. Output power equal to what? Area under output PSD. So what is the output PSD? It is a parabola from where to where? Minus 10k to plus 10k. Which means So it is not omega square into 10 power minus 6. Okay. So what are the limits of this integration? It is because of this low pass filter. Now the limits of this integration are from minus 10k to plus 10k. That's it. Not all frequencies. So minus 10k to plus 10k, 10 power minus 6 into omega square into df. Is it okay? Yes. Now here 10 power minus 6 outside. Omega square means 4 pi square outside. Integration minus 10k to 10k f square df. Is it okay? Now if you do integration 4 pi square into 10 power minus 6 into, so what is the integration of f square df? F cube by 3 from minus 10k to plus 10k. You calculate and tell me the answer. What do you get? So 4 pi square into 10 power minus 6 by 3 into 2 into 10 power 8. Is it right? I am not okay with these calculations. You just do it. Not 2. 10 power 6 only, right? Not 8 maybe. So these two will cancel. The answer is 8 pi square by 3. Is it okay? I am not okay with these calculations. Please do it yourself. I explained the procedure. Calculation you must do it on your own. Okay. So that is the end of the chapter 5, unit 5. Okay. So I will conduct one more quiz. I will inform the dates. So please be prepared. Okay, we stop here. Thank you.